Well, welcome to this academic webcast on JMP for Biostatistics in the Health and Life Sciences. We're going to talk today about how to use the tools and techniques commonly needed by researchers, practitioners, professors, and students in biostatistics and the health and life sciences fields. And specifically, we're going to go through 6 examples today. We'll look at an ANOVA, a regression that has some complicated features involved. We'll look at 2 kinds of mixed models, a split plot design and a repeated measures design, a survival analysis example, and then we'll look at how to actually plan out a designed experiment. We're going to talk about doing this in JMP today, and I'll show you a lot of JMP output. I'll mention how to do these things in JMP, but we're not going to focus a lot on how to use JMP. If you want more information on using JMP, I'll recommend a few webinars and a few resources in a moment. But if you haven't used JMP before, you can see my JMP toolbar sort of fused kind of toward the top of my screen. You can see there's a little apple at the beginning because I screen captured this on my Mac where I'm using JMP. JMP runs on Mac and on Windows, and it works very similarly on both. There's only a couple tiny differences between the two. So for the most part, well, everything I'll describe today, you'll be able to find it in the same places on Mac or on Windows. We're specifically going to use some tools in the Analyze menu. The Analyze menu has to do with the statistics, the statistical models. So we're going to spend a little bit of time in the Fit Model option. We're going to look at ANOVAs there, regression, even some survival analysis we'll find in Fit Model. We're also going to use some tools from the Graph Builder, which is under the Graph menu. This is a very flexible platform where you can drag and drop variables around to create graphics. We'll look a little bit in the DOE platform at the very end for the final example. We'll look at a full factorial design under DOE under the classical designs, but you might also be interested to know that the DOE design diagnostics is where you find power and sample size calculations, and we're going to look at a few other ways to get power and sample size calculations today as well. Then we'll glance at a feature of using tables and stacking data. We're going to look at data for the repeated measures example that's not in the format we want, so I'll show you briefly how to reformat your data. And I'm not going to show you this in the columns, but we're going to do some things where we create a couple of new columns, and so we could use the columns menu to create new columns and then apply formulas or to recode or do things like that. Now, if you have not used JMP before and you want to go back after this webinar and look at some more basics or get a little more familiar with the platforms in JMP, I definitely recommend going to jmp.com/webinar and looking at some of our other academic webinar series webinars. Data summary and analysis is probably a good simpler ANOVA and simpler regression sort of situations, more graphics, things like that. Also, JMP Basics for professors and students is a really good place to get started if you haven't seen anything about JMP before. There are other resources on how to use things or do things or teach with JMP, a lot of exercises and case studies and examples and resources at jmp.com/teach, which is our academic landing page. And then within JMP or online, if you look for the JMP Help Online, you'll find a lot of other resources as well, including the books is our documentation for JMP. And there are lots of examples in that documentation, so you can find a lot of, even some of the examples I'll talk about today, some of these data sets are available in JMP, and you can find more information about them through our help menu. Lastly, I want to point out the JMP user community, which is awesome. If you have questions, you're welcome to email me or other people on our academic team. But you can also post your questions at community.jmp.com and get answers from other users or other people who work at JMP who also like to contribute things on that user community. And so there's lots of resources there. If you're ever stuck and you want to get some help, I would search that community first and see if someone else has asked the same question you have. Otherwise, post it there and give us the opportunity to help you. All right, so let's dive into ANOVA and regression. We're going to look at an ANOVA example where we're comparing pain ratings of men and women taking one of 3 different analgesics. Then we'll look at a regression example about how to predict how long an animal sleeps per night based on some other characteristics of those animals. So for this ANOVA example, you can see the data table on the left. We have 33 patients. We have their gender marked, they're either male or female, and then they're taking one of 3 analgesic drugs, A, B, or C, and then they're rating their pain. Now, just a note about this design. These are pain ratings after they've taken the drug, so maybe an hour later. It probably would be a better design to have taken a pain rating and a post-pain rating to see how much the analgesic is affecting, because we don't know that they're experiencing the same amount of pain. So what we can conclude from these data is going to be a little bit limited, but we're going to use this as our example. So you can see at the bottom of the screen, I'm showing something from the distribution platform in JMP. Just looking at gender, we can see there's more females than males in our data set. Drug, we can see more patients took drug A in our data than they took C, which was still a little bit more than drug B. And we can see the pain, the distribution of the pain measurements. So the average pain measurement was maybe somewhere around 7.5, something like that, maybe 8. We can also see, because I've clicked on the female bar, we can see that females took drug A at a higher rate than males did. We can see that females, on average, their pain measurements seem to be a little bit lower than males. And now if we want to analyze this, we can go to the Analyze menu in JMP and go to Fit Model. And then we're going to get this dialog box. And this is how JMP works, as we see dialog boxes that look something like this. We see there's always a column list here where we can take the variables in our data set and apply them into roles in these dialog boxes. So we're clicking on pain and putting it into the Y role. We're clicking on gender, drug, and gender by drug to create model effects or X effects in this model. And then you can see on the far right side, we have a personality and an emphasis. The emphasis is just how much output do we want to see. So there's an option minimal report, for example, or if I want to specifically call out the effect leverage, I can do that. The personality is the type of model. And so right now we're just going to look at a standard least squares model, but throughout this webinar, I'll show you a few other personalities as well. So this is the output we get when we ask for that standard least squares with gender, drug, and gender by drug as our factors, and pain rating as our response. So I automatically see some visuals to help me understand my model right away. So I see sort of how important is gender effect, drug effect, and gender by drug effect. I can see those p-values on the side and sort of just a sense about how impactful they are. I also see a residual by predicted plot. So right away, I think this is probably okay. I'll look at a few more diagnostics as I go along, but this is a good indication at the beginning that I've got a reasonable fitting model. Then I see on the right-hand side, I've copied the output about the summary of fit. So we see the R squared here is 53%. We can see the mean response was 8.5. We can see the ANOVA table and the overall p-value that something, gender, drug, or gender by drug, that something is making a difference. That p-value is pretty highly significant, so we think there's something going on in these data. And then we see the specific parameter estimates. We see effect tests overall, and so I can see that the gender test is highly significant, drug is highly significant at the 0.05 level, but gender by drug is not at the 0.05 level. And then one great thing in JMP to help me really visualize my model is to ask for the profiler. So the profiler shows me for various factor combinations what my estimated average pain is from that model. So here if I look at the females, so I've clicked on females here in the profiler, and I'm looking at drug A right now, the predicted pain is 6.7845. And the confidence interval on that mean prediction is 5.4 to 8.2. So I can see that on average, females in drug A, I expect by this model for them to have pain scores of about 6.7. I can also see visually from this model the trend for females of the different drugs. And I see those confidence intervals in this profiler. So it's easy for me to see that within females, drug A, B, and C are probably not significantly different from each other. Because those confidence intervals overlap so much, I'm pretty sure that when I do the pairwise comparisons, I'm not going to find differences. If I look at the males in the profiler, so I've now switched over to the males, still looking at drug A as my primary. So that's the estimated pain score for males in drug A is 7.4, so a little bit higher than females. But the confidence interval for that mean prediction is 5.2, 5.3 to 9.7. Pretty wide confidence interval, and it captures the pain estimate from the females. So males and females may not be statistically significantly different in drug A on their pain response, even though males are a little bit higher on average. And then I can see that the male trend A was the drug that gave the lowest pain ratings, but B and C seem to be a little bit higher. And so I might investigate whether those are possibly statistically significantly different. They're going to be kind of borderline because those confidence intervals look like they overlap a little bit. And so I would want to investigate that further with statistical tests. So some of the things I can do from this point are save out the residuals to my data table if I want to look at more plots, or save the predicted values, save out confidence intervals or hats or Cook's D values or leverage values. I might look more at these profilers. There's an interaction profiler to help me see the interactions better. There's a surface profiler if I have multidimensional space and I want to explore that better. I can look at the indicator parameterization estimates if I prefer to see them in that way. You could see that JMP has its own, it's not indicator parameterization. Sequential tests, multiple comparison adjustments. I can look at estimate statements or test contrasts. I can look at testing slices, things like that. Those are all available from those little red triangles at the top of output. I can also look at a retrospective power and sample size analysis. I'm actually going to show you that now. So I might look at the output that shows me the least squares means. So I see the female least squares mean, the male least squares mean, and I see some standard errors and the actual means, not just with the least squares estimation. And then I can ask for things like, do a pairwise comparison between these two groups. And so that when I ask for the pairwise comparison, I get some options about methods. In this case, I only have one pair, so I'm just going to do a student's t-test, and I see some output about those differences. One way I can look at that output is with this connected letters report. I like this report because it's simple and short. If you haven't seen one before, there's a hint at the bottom that says levels not connected by the same letter are significantly different. So the males having an A next to them and the females having a B next to them, they don't have the same letter next to them, so that means the average response for males is different than the average response for females. They don't have the same letter next to them. Then I can do a retrospective power analysis where I can ask for I'm holding alpha constant, but I'm asking for different values of the overall error. So I asked for 2, 3, or 4 for the overall sigma. And the delta, the difference between the groups that I want to be able to detect, I'm also holding that constant here at 1.5. So if I wanted to be able to detect a difference in pain scores, in average pain scores of at least 1.5, depending on what the total overall variation in the data is, I might see a power of 0.7344 if I had a sample size of 15. So a sample size of 15 would give me pretty good power to detect that size difference. If the standard deviation of the data is 2, I'd have almost 100% if I upped my sample size to 50. So I can then see this in a power plot as well. If I look at the drug effects, I can again see the least squares means for the 3 drugs. I can do a comparison. Now if I look at that connected letters report, the A's together here, this is a little confusing because the names of the levels are also A, B, and C. But because there's 2 A's here together for C and B, then drug C and drug B are not statistically significantly different because they have a same letter connecting them. And likewise, drugs B and A are not statistically significantly different because they have the same letter B connecting them. Again, I can look at a power analysis, and I can do the same thing for the interaction effect. So here I can see that male drug C, male drug B, and female drug C are not statistically significantly different using the Tukey on a significant difference criterion. I can see that males drug B, females drug C, males drug A, and females drug B are not statistically significant. And I can see these last 4 categories are not statistically significantly different from each other. Again, I can look at a power plot to see sample size compared to the power of detecting an effect. All right, let's look at a regression example. This regression example is called Sleeping Animals. This is another data set available in the sample data library in JMP. So if you wanted to follow along, you could open this in JMP. This data set has, I think it's 62 species of animals, and the species name is a unique identifier for each observation. And we have information like their body weight, their brain weight, how many hours per day they spend non-dreaming and dreaming in sleep, and then their total amount of sleep, their lifespan, their gestation, and then some scores for predation, exposure, and danger for these animals. And of interest to us is to predict the time that the animals spend sleeping. So one thing I can do is go to the graph builder. So if I go to graph and graph builder, and if I drag total sleep to the response to the Y, if I drag lifespan on one side and gestation on the other side in the graph builder on X, and then if I color these by the exposure, I can see kind of easily that the exposure really matters, that there's higher hours of total sleep per day for animals that have a very low exposure level. That should make some sense to me. If you aren't at high risk, then you can probably spend more hours unconscious. Whereas for group 5 of exposure, those are the fewest hours per day the animals spend sleeping. And I can also see that as the lifespan increases and as that gestation increases, on average, it's a little bit different in different exposure levels, but on average, there's sort of a decline in total sleep. So if an animal has a long lifespan, they aren't going to spend quite as many hours per day sleeping. Possibly, but this is something I might want to test to see if that's a statistically significant effect. So again, I go to Analyze and Fit Model, and I'm going to use total sleep as my Y. And this time I'm going to build a model that's got my X variables I'm interested in, and all the two-way interactions that I'm interested in. So I'm going to click on body weight, brain weight, lifespan, gestation, predation, exposure, and danger. Those are the X's I care about. And after I click on them, you're going to see this macros button under Construct Model Effects. When I click on macros, it's going to give me an option to choose a full factorial, so I could do all of the interactions up to the, 1, 2, 3, 4, 5, 6, 7, 7-way interaction. Or I could choose, as I'm going to do here, factorial to degree. The degree hides underneath, so when I click on this, it'll actually be hidden underneath that little box. But degree says 2. So if I do factorial to degree 2, that'll give me all the main effects and all the two-way interactions. If I change the number for degree to 3, I'd also get the three-way interactions. And then here's a time where we're going to switch that personality. I'm going to choose the generalized regression personality instead of the standard least squares. Generalized regression does two things for me. One, it allows me to change the distribution. If I don't want a normal distribution for the response, I can change that to Poisson or to zero inflated Poisson or binomial or a bunch of different distribution options. Here, that's not why I want to use generalized regression. I want to use it to help me pare down the number of predictors I have. So I'm going to throw in all these predictors, but I'd like to do variable selection on them. And a nice way to do that is with a penalized regression method. So I'll choose this generalized regression so that I have some options for variable selection in a moment. So I get standard least squares output from this. So again, I'm using generalized regression, but I still get the standard least squares output. I just also get more options. So the standard least squares output, I want to focus in on some things here like the BIC and the corrected AIC, the R squared and R squared adjusted. The BIC and corrected AIC, these are penalized versions of that minus log likelihood. The minus log likelihood is how well does this data fit? But these are numbers that are sort of unitless. They don't mean anything until I compare them from model to model with the same data. So I'm just going to keep an eye on BICs and corrected AICs in any models that I run to see how well I'm explaining things. And the ways that they're penalized is BIC and corrected AIC are trying to take into account that every time you add another predictor variable, you're going to explain more. You'll get a better fitting model. But is it worth, let's penalize putting lots of parameters in so that we can kind of have a trade-off between we don't want too complicated a model, but we do want to fit better. So those corrections, the corrected AIC and the Bayesian information criterion, those are helping me sort of balance how many new terms I add as explanatory variables versus the trade-off of how much extra good fit do I get. We can also see some evidence of having way too many predictors in our model right now with that R squared and R squared adjusted. The R squared is 82%, so we're explaining 82% of the variation in the response variable with our explanatory variables. But the adjusted R squared, adjusted for all those extra predictors, is not, it's telling us a slightly different story. It's saying, yeah, you added a lot of extra stuff in here. I'm not sure it's really helping you. So those are just some hints. Those are not hard and fast rules, but just sort of things to look at to help us make some choices. I can also see from the parameter estimates and those p-values, so the p-values on the side, they turn colors when they are less than 0.05 or less than 0.01. So I can see that I've got a couple of p-values that are significant at the 0.05 level. Specifically, exposure seems to be significant, and lifespan by gestation, the interaction between lifespan and gestation. Nothing else came up as significant at the 0.05 level. We can also look at the prediction profiler here. Now that we have continuous variables, instead of just seeing little standard errors around them, we get these shaded areas showing the confidence regions. The fact that basically everything is shaded is a really bad sign. So this model is not a very good model. If you look at this, when the body weight is 224 pounds, when the brain weight is 317, I think that's ounces, when the lifespan is 20 years, gestation period is 142 days, and you've got kind of average predation, exposure, and danger scores. For this hypothetical animal, the total predicted sleep, the average predicted sleep in this model is 3.7 hours per day, with a confidence interval on that mean from minus 33 to 40. So just think about that for a second. There's only 24 hours in a day. So this goes from minus 33 hours in the day, which clearly is senseless, to positive 40 hours in a day, which is also senseless. So this is basically saying, hey, we think this animal is going to sleep about 4 hours a day, but it might be anywhere from 0 to 24. And actually, it might be even, outside of the realm of possibility. So this is not a very good model. We've got too many predictors. We're not actually getting sensible output that's helpful. So this is why we like to use that generalized regression or some kind of variable selection technique, because we might put so many things in the model that it actually ends up hurting us. So one reason that this could be happening is just correlations between the predictors. To look at the correlations, we go to the Analyze menu, to Multivariate Methods, and then to Multivariate. This will show us the scatter plot matrix of those correlations, and we can see body weight is pretty highly correlated with everything. Brain weight is pretty highly correlated with a lot of things, and body weight and brain weight are very highly correlated with each other. So possibly the correlations are part of the issue here. Another possible issue is that maybe we need to take some transformations of some of these variables. Body weight and brain weight are actually good variables to look into further to see if we should transform them, maybe take the log or something like that. We could explore that further as well. But for now, we're just going to use that generalized regression. At the top of that output, it gave us this model launch. So I scrolled to the bottom and we just looked at the output for the regular regression first. But it also popped up this model launch that said, hey, what kind of estimation method do you want to use? What kind of validation method do you want to use? And I have a lot of other options hiding under that advanced controls as well. So if I choose the lasso method, for example, this is a penalized regression method that allows us to put penalties, or to penalize the regression coefficients, and even to penalize them all the way down to 0, so that it throws out some terms. So if it says, hey, your regression coefficient is 0, then that term's no longer really in our model. So it might penalize things all the way down to a stage where it's actually doing variable selection and saying, don't use this variable. And some of those special options we can use here, if we want to make sure that we don't throw out certain terms, we can force certain terms to be in the model. Or if we want to make sure, if this is a designed experiment, it may matter to us that if an interaction term is in the model, that we also have those main effects. So if we need to do things like that, we can use those advanced controls. When I run this adaptive lasso, I'm going to use the corrected AIC as my method of deciding if it's performing well or not. It would be a better idea in practice if I had a large enough data set for me to set out a validation column, but for exploration purposes, this is going to be plenty sufficient. So here I can look at those BIC and corrected AIC again. If I scroll back, In our original model, the BIC and corrected AIC were around 350, give or take. And in this model, we're at around 250, 266 and 279. So in this model, we have lowered those BIC and corrected AIC. We also see a new criterion listed here, the ERIC. That's another criterion we can look at. And here's our R squared again. With these criteria, smaller is better. So the fact that we've dropped these down is actually saying we have a better fit. So we have fewer predictors, so we don't get penalized as much for them, and we have a better fitting model overall, we think. So again, every time you add a predictor, you're technically making a better estimate. You're explaining more variation, but you're not necessarily doing that in a way that's useful or that you're happy about it. So this is telling us, after we sort of consider, we don't want too many predictors involved, this is a better model. These fit statistics are suggesting that this is a better choice. And you can see in the parameter estimates on the right side, a lot of those say 0 in the estimate. And so what's happened is that the model penalized them all the way down to 0 and said, hey, don't even put body weight in the model. Put brain weight in, but don't put body weight in. And don't put lifespan in, but put gestation in. Don't put predation, don't put exposure, but put danger. And then again, we kicked out a whole bunch of these interactions as well. We also see that more things are now significant. So danger is significant, body weight by predation is significant, and body weight by danger is significant. If we look at the prediction profiler, now you see better how those confidence bands look. Remember in our other example, they were so wide that we don't even really see their limits. Now they're skinnier, and this corresponds to a smaller confidence interval on our predictions as well, or on our mean predictions. So now for that same hypothetical animal, body weight 224 pounds, brain weight 317 ounces or whatever that is, gestation 142 days, approximately average predation and approximately average danger, this animal is predicted now to sleep 9 hours a day instead of 3 or 4. But the confidence interval is between 7.75 and 10.6. So we're actually getting something much more useful if we really wanted to know something about the sleeping pattern of that animal. So this sort of looks like it might be a human. A 9 hour, maybe it's one step past us. A cross between a human and what would be the next larger animal in that data set. I don't recall. So this again is a data set that's available in JMP. So if you want to explore this further, it's called Sleeping Animals. All right, let's move on to some mixed models. So we're going to start by looking at a split plot design. Depending on what your field is, you may consider this as a split plot design. That's typically the verbiage you use if you're in agriculture or something like that. Even in engineering a lot. If you're in the social sciences, you're more likely to call this a hierarchical design. Either piece of language is appropriate to describe this type of model. The point is that you have one large unit at the top and you apply a factor at that large unit, and then you subdivide that unit and you apply another factor at those smaller units below. So we'll look more closely at that in a moment. And then we'll look at a repeated measures example as well. So here's our split plot situation, or hierarchical design. We've got a bunch of blocks, so a bunch of these blue ovals. And in these large blocks, we're going to take our first experimental units. So in our particular example, we're actually going to be looking at meat tenderizers, and so we're going to have 6 large pieces of meat, and these are these blue blocks. Within each of our pieces of meat, we're going to take 3 cuts of meat. So these orange blocks, they're called the whole plot. This is where we're going to apply our first factor. So factor A is our high level factor. We're applying it to the large experimental unit. So these orange whole plots become the experimental unit where we apply our first factor. In our example, we're going to be looking at applying tenderizers. So we'll take the large piece of meat, the blue block, we'll cut out 3 cuts of meat from it, and each of those cuts of meat we're going to apply one of 3 different tenderizers randomized to those 3 cuts of meat. Then within those whole plots, the experimental unit for the top level of this, we're going to further subdivide them by, in this case, taking 4 little cores, little tiny bite-sized pieces of meat, out of those tenderized pieces of meat. Those are called our subplots. So those little purple dots are called our subplots. And now we're going to take each of those 4 things from each individual whole plot, and we're going to randomize our 4 levels of factor B to these experimental units. So our factor B in our example is going to be the roasting time that we cook these pieces of meat at. So the orange piece, that cut of meat, gets a tenderizer application applied, and then each of those 4 things from the first tenderizer gets randomized to a different roasting time. So a typical way to analyze a split plot design is going to look something like this. So if you're looking at a statistical textbook, you'll see something like a list of the source of the explanation or the variance that you're explaining, the degrees of freedom associated with that source, and then you'll decide, is this going to be a random effect or a fixed effect? That's what a mixed model is a model that allows us to put some random effects in as well as fixed. It's a mixed effect model, some fixed effects, some random effects. Fixed effects are just treating something like an ordinary effect. Random is when we say, hey, actually, I'm interested in this as an explanation of variance, but not in doing estimation so much on that. So in this case, our top level of block, the 6 cuts of meat, that's typically going to be treated as a random effect. I don't care about the 6 large blocks. I'm not trying to make inference on those 6 specific pieces of meat. I just have 6 pieces of meat, and I know there's going to be some variation from piece to piece. So that's the block, and it's probably random. Then I'm applying factor A, the tenderizer, on some experimental units out of that block, so the whole plot experimental units. Factor A, I do care about comparing my different tenderizers to each other, so that's a fixed effect. Then if I take the interaction between those 2 things, that's going to be the error term that I test blocks or test my treatment A on, and so that's also going to be treated as random. Usually, if you have something treated as a random effect and then you put an interaction with that into the model, that randomness is sort of like a disease. So most experimenters will say if blocks was random, then blocks interacted with anything else is also random. So it travels like a disease. If the blocks is diseased, it stays diseased everywhere it goes. So probably we'll treat the blocks by A as random, and this is particularly critical here because if we want to use that as an error term, that needs to be something where we're looking at the variance and random effects. We're interested in the variance. Then below that level, at the smaller level of our study, we've got the B effect, in our case, the roasting time. And then we could also look at the A by B interaction. Both of these things, the experimental unit will test them against is the tiny little purple dot, the smallest experimental unit, and that will be the actual error left over from our whole model. So this same experiment could describe a lot of different situations. So we might look at something like applying different nursing methods within hospitals. So first, the 6 big blocks, the blue blocks at the top are 6 different hospitals. Then we look at 3 different units within those hospitals. So those are the whole plots. And we apply a nursing method to each different unit. So we ask all the nurses in one unit to use a certain method. Then within that unit, we have the patients, which are the subplots, and we ask them to rate their satisfaction using some different rating scales. So something like that would be the exact same situation. It's a hierarchical design or a split plot design. Or another option would be that this could actually be an agricultural split plot design in plots on fields. So our high level, the blocks might be different farms. Then we're splitting them into large fields within the farms. Those large fields each field gets a different watering method. Then within the field, we have smaller fields or subplots. And then on those subplots, we're applying 3 different fertilizers. And then measuring the yield. Or in the case we're looking at tenderizers applied to these cuts of meat within the different carcasses, but different roasting times are randomized to those little subplot cores in the cuts of meat. Okay, so here's how we analyze that. That little table on the top right is a key to how we need to enter these terms in the model. We need to enter the block term as random. We need to enter blocks by A as random. We need to enter A, B, and A by B as fixed. So A, B, and A by B are the tenderizer effect that was applied at the top level. the roasting time that was applied at the bottom level, and then their interaction, those go into the fixed effects. I'm now using the personality mixed model up here because that's going to give me a random effects tab to use and also a repeated structure tab, but we don't need that right now. So then on the random effects tab, I'm going to add the carcass, that was the blocks, and carcass by tenderizer, that's the blocks by A. So this is all you need to know to analyze this split plot type of design. You've got to identify ahead of time what is your factor A, what is your factor B, what are your top blocks, and then you just put A and B and A by B interaction as fixed. You put your top blocks and your top blocks by A as random. So this is a standard, very typical split plot design. If you've got a version of this, a variation of this, then follow your statistical training on how you're going to update which things go into which of these boxes. So the first thing we could look at with the profiler is if we are looking at the control tenderizer, the roasting time 30, the response was toughness, and so if you don't roast it very long, it's very tough. If you roast it a little longer, it's still pretty tough, but then once we drop to 42 and 48, those are the best responses here. If we look at the second tenderizer, we can see that did much better, much less toughness. That's actually the best response here. And again, it drops the longer we roast it. And then the vinegar treatment looks very similar to the control. At 30 and 36 minutes, it's still pretty tough. And at 42 and 48, it's quite similar. So those two times, it's sort of, did you roast this less than 40 minutes or more than 40 minutes? If I wanted to visualize this in a three-dimensional space, I can ask for the surface profiler just to get a little bit, a picture with more dimensions in it. And here's what the statistical output looks like. I see things like the actual by predicted and actual by conditional predicted plots to help me see if this looks like it's a model that fits well. I see some fit statistics like the corrected AIC and BIC again. I see aspects of those variance components. So everything we put in the model as a random effect, we're estimating a variance. So we have that total variation at the bottom, we have residual variation, and then we have the carcass and carcass by tenderizer, the blocks and blocks by A variance components. We're allowing negative estimates for variance components. Don't think about that too hard, because a negative variance, that's nonsensical. But this is a standard practice. So again, if you want to change this, there was a selection box on right under the personality. It says unbounded variance components, and so you can change this if you don't want to allow negative variance components. And then we can also see the specific random coefficient. So for each of our 6 blocks, we can see that the first 3 all had higher than average overall effects. So higher than average toughness for the first 3 carcasses and lower than average toughness for the last 3 carcasses. So that's just interesting to note. We can see the carcass by tenderizer effect as well. And so we can explore any of these pieces a bit further. And then we can see the fixed effects parameter estimates, the standard sort of output we expect to see for all the fixed effects, where we see the estimates and we see the p-values associated with those. And we can see the fixed effects tests. So in this case, our factor A tenderizer, our factor B roasting time, and our interaction between those are all highly significant. Then we can also do some more follow-up comparisons. So maybe we want to do least squares means estimates as multiple comparisons. We can either do it on tenderizer or roasting time or the interaction. And we have options of how to adjust that. For example, do all the comparisons against a control, or do the Tugis on a significant difference to adjust them if we wanted to do just all of the pairwise comparisons. If we chose user-defined estimates, then we can set up estimates to, for example, look at control at roasting time 30 versus the other 2 tenderizers at roasting time 30. So we can set up our own user-defined estimates as well. And again, we can apply adjustments if we want to. Okay, so let's move on to the repeated measures example. In this example, we're looking at cholesterol drugs. So we've got 2 new cholesterol drugs, and we're comparing them to a control cholesterol drug. We've got 5 patients with high cholesterol that are randomly assigned to each of the 4 treatments, so 2 experimental drugs, control, and a placebo. And then the patient's total cholesterol was measured 6 different times during the study. In April, on April 1st in the morning and afternoon, on May 1st in the morning and afternoon, and on June 1st in the morning and afternoon. And our interest is whether either of the new drugs is effective at lowering cholesterol, and we want to see if the time and treatment interact. So does it take more time for one of the drugs to work than it does for another one? When you have repeated measures data, the special thing about this is that your measurements are not totally independent of each other. So normally in statistics, we say that we want our responses to be IID, independent and identically distributed in a certain way. And we are breaking that assumption here. We know already. A lot of times we break assumptions, but we just don't realize it. In this case, with the repeated measures, we know there's going to be correlation within a patient on their measurements. If I have high cholesterol, I'm probably going to have high cholesterol for most of the study. Even if the drug helps, it's starting from a higher place that it has to help me. So since we don't have this total independence and we know it, if we really want to do this correctly, we need to account for that. So we want to account for those correlations within subject. Now is the moment I'm going to sidestep also and take us back to the tables menu in JMP to do something special. So if you wanted to follow along, there are two data sets in JMP for this situation. One is called cholesterol.jmp, and I'm showing you that on the screen right now. That's in the wrong format. So if you had done this study and you collected your data in this way in a spreadsheet, where you had treatment A, there were 5 people. Here's their measurements in April in the morning, April in the evening, May in the morning, May in the evening, June in the morning, June in the evening. This is a perfectly reasonable way to keep this spreadsheet, and it keeps it only 20 rows long. It's easy to see what's going on, but this is not the way we're going to need it in order to analyze this for a repeated measures experiment. So what we want to do is stack the data so that we just have one column with the response. We need the cholesterol measurement to be a unique column, one column, not 6 different columns. So the operation we need to do here is stacking the data. So if I go to the tables menu in JMP and I choose stack, it's going to turn it into something that starts to look like the other data set in JMP called cholesterol stacked. So here's what we do. We go to the tables and then stack, and then we click on the April AM, April PM, May AM, May PM, June AM, June PM, and put those into the stack columns. That's what we want to stack on top of each other. That's all we have to do. Then I can name the output table something if I want to, so I'm going to call it cholesterol stacked, and I click OK. So this is what I get. Now it's put the April AM on top of April PM, on top of May AM, on top of May PM, on top of June AM, on top of June PM. So now the data column is my response, and the label column is the time, and the treatment remains the treatment. So now I need to rename some of these columns. I just click in them to rename them. And so I also need to add some variables into the cholesterol stacked to help me describe the month and the time of day separately. So if I want to do this, I can use some formulas. So if you've never used formulas in JMP, they're really easy to use. So what I've done here is I'm creating a new column. So I went to columns and I said new column, or else I just double clicked in a new column and it will pop up this little box. It'll say, okay, your column name is going to be what? So I'm naming it month. And then I'm applying a formula by going to the column properties with that little arrow and saying, yeah, I want a formula. And then when I edit the formula, I get to type in the formula I want. There are so many things to help you with figuring out how to write the formula. In this case, the formula I want is I want to take the label column that says April AM, April PM. First, I'm going to rename it time. And then I'm going to take out the first word from that. So April is a word, then there's a space, and then AM is the second word. So this function, word, pulls out the first word from this. This is super useful if you're needing to pull out separate variables from one kind of concatenated, smashed together variable. That word function is really useful. So I'm taking out the first word from that label column, which I'm also renaming time. And then I'm going to make an AM PM where I take the second word. So we'll see the results of this in a moment. The third variable that I need to make a formula for is I want to make a days where it's actually a numeric. I want a continuous variable. This is critical because of doing this as a repeated measures. Some of the repeated measure structures require the time to be a continuous measurement. And all I've got right now is April AM, April PM, May AM, and May PM, etc. So I need to turn that into time. So here, if I do this match function, or if I just used a recode under columns, I can say if it says April AM, call that time 0. If it's April PM, call that time 0.5. It's halfway through that first day. If it's May AM, call that day 30. If it's May PM, call that day 30.5. If it's June AM, call that day 61. If it's June PM, call that day 61.5. So now the end result of me making these 3 new formula columns and renaming label to time is I have the patient listed at the beginning. Then I have the response, Y, that was the data column. Then I have the treatment. And then I have the time column, the month, the AM, PM, and this new continuous days. So that's the table that I want to use to do this analysis. So repeated measures, a couple special things. 1, we know they're not independent. 2, we need a stacked form of the data. And 3, we might want a continuous version of the time, depending on the structures we want to try. Okay, so let's look at exploring just what's in these data. So if I look at the time measurement, the days, that continuous measurement on the x-axis and cholesterol on the y, I can see for each patient is a separate line and they're colored by their treatment group. So I can see placebo and control, nothing really happened. So the control drug doesn't really work, does it? It doesn't seem any different than the placebo. So across all the times we measured cholesterol, the placebo and control stay pretty much the same. Treatment A and B, they get better. And specifically, after 1 month, treatment A really gets better, and then it improves a little bit more by the end. And treatment B seems like it's not as good at 1 month, but at 2 months, it's pretty close to treatment A, maybe the same. We can also see these little sort of like jigs from day 0 to day 0.5, from day 30 to 30.5, and 60 to 6 or 61 to 61.5. Those are the AM to PM measurements. So we can see that every day people's cholesterol is lower in the morning and then higher in the evening. So that's interesting. Makes some sense. I haven't eaten when I first wake up. Okay, so when we fit this model, we're again going to go to Analyze and Fit Model. And we want to fit the full factorial of the treatment, the month, and the AM by PM. And so we're choosing mixed model as our personality. We're putting those fixed effects into the first box, so that full factorial of treatment, month, and AM, PM. Then for the random effects box, I don't put anything in there because this time I'm not trying to treat anything as a random effect. I could, but I'm not going to right now. And for the repeated, here's the important thing for repeated measures. I need to say some kind of structure for this. So in this case, I'm going to call it unstructured. The unstructured says for every single pair of times, estimate a specific correlation for that. So everyone between their first measurement and their second measurement, estimate a correlation for that. Between their second measurement and their third measurement, estimate a correlation for that. Between the third and the fourth, estimate a correlation for that. So unstructured is going to create a ton of new parameters. So just like our regression example we looked at with too many parameters involved, that may be a problem. So we're going to do this first because it gives us the most information to make other decisions, but this is not usually the final model. Unstructured estimates everything distinctly, and it's not usually the best model. Okay, one other note, we might actually add a random effect later on. We could add the patient as a random effect because the specific patients in this data set, maybe some patients had high cholesterol, some patients had low cholesterol. So each person has their own sort of randomness they're bringing to this. So we could put patient as a random effect, but we're going to have a problem while we do this with unstructured. So we'll wait and add that in later. So when we run this with the unstructured, we get a list of all those variances and covariances. So the variance for just April has its own estimate of 18.7. The covariance between the April in the morning and April in the evening has this estimate of 18.35, and so on. Now, this is a little bit hard to follow what's going on to really see a trend. So what I like to do is right-click inside of this data table. So anywhere I hover my mouse inside of this data table and I right-click, and I say make into data table. You can always do this with any output in JMP. and it might make it easier for you to pull it out into Graph Builder and do something with it. So I'm making this into a data table so I can take those estimates and plot them. So what we see here, and I have to point out there's a small mistake here. This should be time 0 and time 0.5. I called it time 1 instead. But the blue line is saying this was the April morning measurement. The red line is the April evening measurement. The green line is the May morning measurement, and the purple line is the May evening measurement. And so we're looking from time 0. So the April, May is here at time 30, and June is here at time 61. So for April compared to April, there's really high correlations between the morning and evening measurements. With May compared to May, there's really high correlations between the morning and evening measurements. So the morning and evening measurements are very highly correlated with each other. On the other hand, here, these correlations of 0.2 to 0.4, these happen between May measurements and April measurements. So April and May are not very correlated. There's a little correlation, but it's between 0.2 and 0.4. And then these measurements are saying the April compared to June. These are almost zero correlations, really low. So what we can see here pretty clearly is as time passes, those correlations are decaying. And so that's really helpful information to help us choose a structure. One structure we could choose is just unequal variances. This is not doing anything about the correlations. It's just saying, hey, but maybe you have unequal variances at the different time points. Another option is the compound symmetry, which assumes you do have a correlation, but it's exactly the same across time. So that is not what our picture shows. Our picture does not show straight lines across time with the same correlation all the way across the plot. It shows a decay. So unequal variance is probably not the right choice for us because we do have correlations. Compound symmetry is probably not the right choice for us because we have correlations that are decaying. The correlation matrix that would make sense for compound symmetry would just have the same correlation everywhere that's not, with itself. We could also do a compound symmetry with unequal variances. But again, these are not things that match the situation we have. What does match our situation is the AR1 structure, or autoregressive of order 1. This structure assumes that the correlations will degrade, specifically that they'll degrade exponentially over time. Every time we change by 1 time unit, they're going to degrade exponentially. So the AR1 says when you're 1 time unit apart, maybe your correlation is 0.9. When you're 2 time units apart, now it's 0.9 squared. When you're 3 units apart, now it's 0.9 to the third. So you get smaller and smaller correlations as time passes. So these are the methods I think we should explore. Let's look at just a residual only method. That's nothing. That's doing nothing for the repeated measures. That's pretending we don't have repeated measures, and we know already that that's a bad idea. Let's try compound symmetry. And compound symmetry is actually just going to be using patient as a random effect. Compound symmetry, again, doesn't take into account our correlations. It says there's just one correlation across all the times. So probably not a great idea. AR1, though, that's maybe a good idea. And we could also do a variation of AR1 where we put patient in as a random effect as well. And then we have the unstructured we already looked at that we can compare to these other methods. So we think AR1 or AR1 with the patient as random effect are probably going to be the best methods here. Okay, so the unstructured was the most complicated. AR1 plus random patient effects was the next most complicated with the number of parameters, then the AR1, then the compound symmetry, then the residual only, so doing nothing to account for any of this. So if we look at those fit statistics, and let's specifically look at the corrected AIC and the BIC, for the unstructured, they're in the 700s. For the AR1 plus the random patient effects, they're dropping, so it's the BIC is still in the 700s, but much lower. The corrected AIC is now in the 600s. AR1, same story. Compound symmetry, that went up to 800s, and so did the residual only. So, in fact, the unstructured fits better than residual only or compound symmetry, which are not taking into account the correlations. So the unstructured, by taking into account correlations, helped. It did a lot better, but it's over-parameterizing. So actually in the middle of this, the AR1 with the random patient effect or AR1, these are our two options that are good ideas. And specifically deciding between them, they're really similar. So it doesn't really matter in this case. Those are very, very close numbers to compare between the two. But technically, if we were going to pick one that fits the best, the AR1 fits the best in this case. It's a little bit better on those fit statistics. Smaller is better. So our AR1 is our winner here. If we had some reason to want to include the random patient effects, that's not an unreasonable option. Okay, so if we just explore those a little farther, the AR1 model, if we look at the fixed effect parameter estimates, we see these standard errors in denominator degrees of freedom. Notice those denominator degrees of freedom are different in the AR1 versus the AR1 where we put the random patient effects in. So you can see there is an impact of having more parameters. When we have to estimate all those, each patient gets a random variance associated with it. So there were 20 patients, I think. So that means we have 20 new variance estimates that we have to make. When we do this, it's going to impact how the degrees of freedom get distributed for these tests. And so it changes the sample size that we're allowed to sort of use to test these guys. So really there's two things that happen. Those standard errors are impacted by the degrees of freedom, which is sort of the sample size that's left over for us to use. But they're also impacted by the error component. So if adding the random patient effects explains a lot of variance, then that might be worth it. So we take away degrees of freedom, but if we add a lot of explanation, it might be worth it. And so that's why we're looking at the balance of adding parameter estimates versus how much we're able to explain. Because if we add model complexity, but we reduce that unexplained variance, we will actually get better detection of significance. On the other hand, if we don't gain enough in explaining the variance, losing those degrees of freedom will make it harder to find significant differences. So that's why we're looking at these fit statistics and trying to really decide what's the best fit, and do we want to add more complexity? Is that going to help us, or is it not helping us? So in this case, adding the patient random effect doesn't really help us. So that final model with the AR1 structure without the patient effect, we can look at the residuals plot. Again, we can do multiple comparisons between those fixed effects. So we could look at the treatments. We could compare the months to each other, AM and PM to each other, any of those interactions, set up our own estimate statements, and so on. And let's look at the profilers. So this is the whole reason that we do a repeated measure structure in this way, is to shrink those confidence intervals so that we actually can find statistically significant differences appropriately. We don't have that independence. So if we can try to explain it, anything we can explain helps us to be able to better detect differences. So here we see in the top plot for drug A, we saw in April there's no difference yet. They just started taking it, but it drops dramatically in May and June. For drug B, we already know that story is going to be similar, but just not quite as fast a pace. Okay, let's move on to survival analysis. We've got this and one more topic to cover today. Survival analysis could be treated again as a generalized regression. So I'll show you a couple ways to do survival analysis. One option is using the survival platform. Another one is using a generalized regression. So in this case, we're going to use this rats data. An experiment was undertaken to characterize the survival time of rats that are exposed to a carcinogen in two different treatment groups. And we're looking at when they die. So we're tracking them for a number of days. And that censor column, failed or censored, failed means they died. And censored means the last time we kept track of them at day 204 for rat number 11, that rat was still alive. We didn't know what happened yet. And our objective is to see whether rats in one of the treatment groups live longer than rats in the other treatment group. We also have an extra column in this data set called the failure cause. We're not going to use that today, but that might be interesting as well. Okay, so if we explore the distributions, we can see, for example, if I just look at the censored rats, so these are the ones that were alive the last time we checked on them. They seem to be equivalently in group 1 and group 2, but group 1 was bigger, so smaller proportion for group 1. And we can see those are the ones that seem to live longer, or at least at the very top of the data set. We can look at things like box plots to see the distribution of days of survival for group 1 versus group 2. So do you think group 1 is better days of survival? It seems like the mean is a little higher. So maybe group 1 is going to be better. That's what we're going to test in a moment. We can also look using the tabulate option in JMP. We can make tables really quickly. So here we can see for group 1, we can see 2 survived to the end, 19 died. For group 2, 2 survived to the end, 17 died. And we can see the min and the mean and the max of the days of survival. So to do this analysis, we have 2 options. We can either use analyze fit model or analyze reliability and survival. So if we go to reliability and survival, there's an option just called survival. And this is what that dialog box looks like. So the Y in this case is time to event. So we put the days in as Y. We put group in for grouping because we've got the 2 groups to compare. We put sensor in for sensor because that's the variable that says if they were alive or dead at the end. And then we can see in the bottom left-hand corner, there's a place to put a sensor code. This says that the ones were the ones that had been censored out. Okay, so here's our survival plot for group 1 and group 2. Group 1 is the one that has slightly higher days on average, and we can see that visually here. So we see the percent surviving as time passes on. So the red group 1 line is on the top, and the blue group 2 line is on the bottom. This is the Kaplan-Meier survival curve. We also see the sort of life table. It's specifically the Kaplan-Meier version of that. Right below, we see that for group 1 and for group 2. So we see at day, for example, 142, 95% are surviving, 5% have failed. And we can see specifically 1 rat has died at that point. None of them have been censored yet, so we didn't lose track of any of the rats yet. And then because we had 21 in that sample at day 142, before we saw the 1 died, there were 21 at risk. So we can see for group 1 and group 2, these life tables, sort of the Kaplan-Meier version of a life table. We can see the same thing for the combined. So if we don't want to split it into groups, we also see the combined. And then we see a summary. So the group 1 average was 240 days. For group 2, it was about 219. And combined for the 2 groups together was about 231. We can see quantiles, like that for group 1, the median time was about 233 days, and we get a confidence interval on that. For group 2, it was about 216 days. We get a confidence interval on that. And for combined, we can see those are really close to the means reported above. So means and medians are very close in this case. From quantiles, we also see that 25% of the failures happened for group 1 about day 232, and 75% happened around day 280. And for group 2, that was 190 and 234. So the days that 25% had died by day 190 and 75% had died by day 234. And we also saw 2 chi-squared tests to test, are the 2 groups different? Are the survival times between the 2 groups different? Based on the log rank p-value of 0.0772 or the Wilcoxon p-value of 0.1035, we have to conclude that no, there's not statistical evidence of a statistically significant difference between the survival times for group 1 and group 2. Now, if we wanted to look further into estimates of how long we expect rats to survive or to estimate how many rats will die by a certain date, we can use the life distribution or fit life by X options. So I'm going to use fit life by X because in this case we might use group as our X. So I'm going to put days as the Y, I'll put X as the group, and I'll put sensor in as sensor. I'm going to select a Weibull distribution to begin with. I'm going to have the option to look at different distributions and compare them to the non-parametric in a moment as well. So the first thing I get to see is comparing how well these distributional assumptions fit the actual data. So you can see those smooth confidence interval bands. Those are from the Weibull distribution estimation, and they're capturing the data really nicely. So the Weibull does seem to fit pretty well. The boxy estimates in the background were the confidence intervals for the Kaplan-Meier situation. So if we're willing to make a distributional assumption like the Weibull, we're going to get tighter confidence intervals and better estimation on things, and so smaller confidence intervals on estimation. So if we use the Weibull and I use the Fit Life by X platform, I can do things like get custom quantile estimation. So if I want to know what's the time at which 10% have died in group 1, that time is 176 days. And how about group 2? That time is 155 days. If I want to know when 50% have died, for group 1, that's 249 days. For group 2, that's 218 days. And I also see confidence intervals on that. It can do the same thing with probability estimation. So for at 200 days, what probability, what percent of the rats have died by 200 days for group 1? That's about 20%. At 200 days, what percent of the rats have died in group 2? That's about 35%. How about at 300 days? For group 1, that's about 86%, and for group 2, that's about 98%. So any of these kind of things that I want to do with a survival analysis are available specifically in the fit life by X. On the other hand, if I have a more complicated model and I want to add more predictor terms, so not just one X variable, but many X variables, or if I want to do modern variable selection using the lasso or elastic net or things that I showed you before, we can do this using the analyze and fit model. So if I choose generalized regression, I get those lasso kinds of things for variable selection. If I choose parametric survival, I'll just get sort of the fit life by X options, but with many X variables. Or proportional hazards is the Cox proportional hazards model, which is a semi-parametric model. So that's available there as well. All right, and our very last topic is about designed experiments. In many cases, you've already designed your experiment, you've collected data, you've got a data table, and you're ready to analyze it. And in that case, you would just follow what we do for ANOVA, regression, those sort of things. But if you are at the design stage and you want to use a statistical tool to help you set up the design, to help you do the randomization and so on, JMP is a great tool for that. So if we had the plan to measure the yield of plants, we're going to give them either a high or low level of a fertilizer treatment, and we're going to either put them under drought conditions or they'll be well watered. I want to run this as a balanced full factorial design, and I'm going to put 4 experimental units in each of those treatment combinations. So I want 16 plants total. I would go to the DOE platform. I would choose the classical option to get a full factorial design. The custom designer is awesome for situations where you don't want to use all of your design space, or you've got something more complicated, or you want to sort of balance your resources and figure out how many what your sample size should be based on your resources. But in my case, I know exactly what I want. I want a full factorial design, and I want 4 experimental units in each combination. So to set this up, I start by typing a response name. So I could call this yield, for example, and I'm going to leave the goal as maximize. I want to get the biggest yield. Then I go down to the factors. In my case, I've got 2 categorical factors. So where it says add n factors, I type in 2. I click that categorical button and it'll give me 2 level as an option. So that's how I chose these guys. And then I can enter in information like change their values to low and high and drought and well watered. I can change the names from X1 and X2 to something else. When I'm ready, I click continue. And then I have this extra piece of information that pops up in the bottom of my dialog box that says, hey, do you want me just to run this, to randomize this with 4 runs? Or do you want to add some center points or replicates? So I've typed in the number 3 for the number of replicates because I want 4 experimental units in each combination. So that means an original one and then 3 replicates. So does that make sense? You want 3 replicates of the original thing. So that's a total of 4. And then I click on Make Table, and it gives me this JMP data table that's got the pattern at the beginning that says for your X factor 1 and X factor 2, are you low and low, and then low and high, and then low and high and low. So then I also get the variables X1 and X2, and I get a spot to put my response into. So there's my 16 observations, and my data table is already set up for me. I also get these 3 scripts saved in my data table. The DOE dialog will just take me back to where I was a moment ago with this thing. The model we'll look at now. So the model, if I click on model, it's going to take me to fit model. And it's already going to pre-populate the yield as the response and the model that I asked for X1, X2, and their interaction, the full factorial. It's going to set it up as a standard least squares. So it knows, how did I design this? Let's pre-populate the fit model dialog with the way you designed this study. If I chose the evaluate design, then I get some options like this. Design evaluation lets me do a power analysis ahead of time. So I can say, what if I anticipate that the effect of X1 is if I go from the one fertilizer to the other, there's going to be a 3 times different. So I can change that anticipated coefficient to 3 and see how my power to detect that changes. Or I can alternately look at the design and anticipated responses and say, what do I expect to get as the responses for these things? And that's going to, if I click apply changes, it's going to change these coefficients based on what I've put down here. So I have a couple ways to think about what results do I expect? What kind of differences do I want to detect? And then it'll give me the power analysis based on those. I can also look, among many other things, as I evaluate this design, I can look at the color map on correlations. This is showing me that x1 with x1 is a correlation of 1. Of course, with itself it's 1. x2 with x2 is 1. x1, the interaction with itself is a correlation of 1. And everything else are uncorrelated, completely uncorrelated. They're 0. If I had a design that wasn't a full factorial, I might actually have correlated effects, and so I would be able to see that with this evaluate design. One other piece of information that could be really helpful when you're designing this, so if I'm in that original DOE dialog box, if I click on that red triangle hotspot at the top, I can select simulate responses, and then just keep going through, click continue, set up my design, make the table. If I ask for simulate responses before I make the table, when I make the table, it's going to give me that same factorial output like I did a moment ago. But now it's also going to give me a column that says yield simulated, and it's going to give me this pop-up dialog box where I can type in different effects, sizes, or even different distributions if I've got a different situation, so that this is actually a formula column where it's simulating the yields based on what I'm saying the model is. It's also copying that into yield. This makes it easier if I do want to do a power analysis with a randomization or something like that, or some kind of simulation. Having a simulated column is going to give me far more options. There's so much more that you could learn about this that I can't possibly cover today. So I do want to draw your attention to a few other places to go for more resources. One topic that I think comes up a lot when I talk to biostatisticians or health and life sciences researchers is how to use JMP with SAS, with R, with MATLAB, with Python, how to capture real-time data. So you've got an instrument that's capturing data and you want to get that into JMP directly. If you go to our JMP help, either in the help menu where you look under books or just search online for JMP help, under the scripting guide, there's a topic called extending JMP, and that will tell you how to use JMP with these other extendable ways. Just a tip, the JMP connection with SAS is a little bit more intimate than some of our other connections because we're the same company. So some of these platforms you can actually generate SAS code out of, and you can set up a connection with SAS and run things in JMP, send them to SAS, run them in SAS, bring them back into JMP, and so on. So there's a lot of really cool things you can do there if you're interested. Also, power and sample size is really critical when you're in biostatistics and trying to figure out how many patients will you need to enroll, or in an ag study, how many plants do you need in order to be able to actually get the value out of your experiment? So I tried to show some of that in this webinar today, but if you want more information on this, if you go to jmp.com/learn and find the basic proportions and means section, that's going to have a couple of just simple one-page guides about how to do some simple power calculations in JMP for, comparing means or comparing proportions. Or if you want to do something more complicated or learn more about what was in that DOE, again, go to the help menu or search the online JMP help. Look for the design of experiments guide and this topic called prospective sample size and power. And we've got tons of things on our website all over the place. So many examples and topics and videos and things. If you want to watch some other videos on very specific topics like text mining to find insights in patient charts or things like that, or more about generalized regression, more about survival analysis, more about designed experiments, search online for JMP on-demand webcasts, and you're going to find our listing from our main JMP webpage of just tons of really great examples. So thanks for joining me today. I hope this was useful. Please do get in touch with our academic team if there's any way that we can help you. Good luck.